this is the second proof. Remember in the previous lecture, we were able to say, we were given that if x minus z is v and x plus z is u, then we solve simultaneously to obtain x and z. And we obtain x to be this and then z to be this. Okay? Then in the first proof, remember we had the first proof earlier in the previous lecture. We substituted u for whatever we have here and then v for whatever we have here. Then x, u plus v over 2 for whatever we have here and u minus v over 2 for whatever you have here. So we are going to do exactly the same thing here. Okay? Since we already know what u is x plus z. Then you say cos x plus z. We can always say substitute star. Okay, you know this is star, this is star. We can also call this star. We can also call this star. You can always name yours A, B, C, D. They say substitute star, and then star. In this equation, you can call this equation 1 in equation 1. Remember they said we should use star and star to prove that this is equals to this. Then we were able to produce star. Okay, then we will substitute star into this equation 1. Then this is equation star minus cos v was originally what? X minus z equals to 2 sine u plus v over 2 was x times u minus v over 2 was z, sine z. Okay, and by the time you multiply this together, you get 2 sine x sine z. This is more or less like what we proved earlier. The earlier one was divide both by 2 here, then it will be half of this equals to this. Okay, so it's more or less the same thing. Okay, from here we are not going to go from LHS to the right hand side here. We are going to go from the LHS. We are actually going to go from the LHS to the RHS. We are not going to go from the RHS to the LHS like we did earlier. Okay, then we say from the LHS, we can always expand this. Remember the LHS is this. We make use of our compound angle formula. We expand this. We say cos x cos z minus sin x sin z minus, okay, let's keep this in bracket, minus into cos x cos z plus sin x sin z. Okay, let me just put it here, sin z. Okay, then from there we'll open the bracket using minus there. We have cos x cos z minus sin x sin z minus cos x cos z. Okay, by the time I open that, I'm going to get minus sin x sin z. Okay, from here this will cancel. I'm hoping something is wrong with that question. Okay, this is x plus z here, x plus 2 here. Okay, I think this should be negative. Okay. Then from there, that will turn this to positive. Minus, then this should be positive. And that will turn this to negative. Okay, as you can see, this is the way the question is meant to be. Cos x minus z minus cos x plus z. Okay, definitely it should be cos v minus cos u. Okay, so we can say cos v minus cos u is that. So I want to show that where v is x minus z. Okay, I will say x minus z, and u is x plus z. Then from there, we expanded this. You know, when you expand this, cos x cos z plus sin x sin z. When you expand this, you have cos x cos z minus sin x sin z. So by the time you open the bracket using the minus z, this, you negate this, then this will be positive. This will be positive. You know, originally this was positive, this was negative, and this is expected to be positive, and this is positive too. So by the time you add these two together, this and this will vanish. It will be equal to 0. By the time you add these two together, you get 2 sine x sine z, which was what you were meant to get here. Then you can say hence cos v minus cos u is equals to 2 sine u plus v over 2 times sine u minus v over 2. So we're able to show that this is this, since you were able to generate this to be this. You can always do the third one. You can always try it on your own. It's something very simple. So from here now, since our aim is to get into calculus, we've discussed the elementary aspects and some other aspect of trigonometric function with the graph. But now we are going to enter into introduction to calculus. Without limit of a function, we cannot talk about calculus. We must learn how to limit a function. How to limit a function to a particular value. So we can have limit of functions. Limit of functions. Limit of functions. When we started this lecture, the first lecture, I discussed how functions are related to mapping. And then we have mapping, functions, their relationship. Okay? So, what if we now start substituting values? Imagine when you have a situation whereby you say something like f of x equals to 2x plus 3. And then you say, keep on substituting the value of x. Say, when x is 1, f of x is 5. When x is 2, f of x is 7. Like that. When x is 1 million, you always obtain a value for this. Okay? But we can say that in the real number system, we cannot exhaust all the values for x. Since we cannot exhaust all the values for x, and that's where limit of a function comes in. Okay? If x tends to a particular value, let's assume that x tends to x naught. What will f of x tend to? Then to tend to f of x naught. So if I say, okay, where if x tends to x naught, f of x tends to f of x naught, then you can always say, f of x is originally, this is your left hand side, this is your right hand side. You can always say 2x plus 3 equals to, what do you have here? 2x naught plus what? Plus 3. So if I give you a question like, you remember that f of x is 2x plus 3. Say 10x to 2. Then what do you say? Just input the value of 2 here. What they are saying is, put 2 here and say 2 into 2 plus 3. I say 4 plus 3, and the answer is what? Is 7. So limits of a particular function, if I set the value of x to be this, where will the function tend to? Okay, let me give you another example. Actually, these are simple examples. Okay, we can always have, remember earlier, I gave you something like y equals to tan theta. Tan theta. As at any value for theta. When theta, by the time theta is now 90, there will be no value for this function. That's another aspect of limit. Okay? Let's have this. Limits. There can be limits for a particular function at a particular point. When I say a particular point, then I mean point x. When I say a particular function, then I mean f of x. Okay? Unlike this, if I set this to be y is equals to tan x, when x is 0, y is 0. When x is 45, y is 1. When x is 180, y is 0. But when I set x to be 90, then this vanish. I'll be able to cut it on the graph. Okay? Then I can say, to every y is equals to tan x, x can be found in all degrees except what? Multiples of 90 degrees. Okay? Now imagine if you are given function like y is equals to 3x plus 7, and I say limit x to 5, y is equals to 3x plus 7. Then what do you say? You say limit of this, you have y, limit of x to 5, 3x, plus limit of x to 5 to 7. And by the time you put 5 here, 3 into 5 plus limit of a constant is a constant, 7. 3 times 5, 15 plus 7. And when you, by the time you add 15 to 7, what do you get? You get 22. And the limit as x tends to 5 here, this function is tending to 22. That's what it means. Okay? Imagine a situation whereby I gave you function y to be 1 over x, and I said limit x to 0. Okay, as at 1, 3, 4, 5, 6, 7, 8, 9, I can always have something. Then from here, I said 1 over 0. What do you think will happen? 1 over 0 is infinity. I cannot put this on the graph. Actually, the limit exists, and we're still going to check how to find the limit of this kind of function. Okay? Let's see some simple laws. Simple laws of limit. Simple laws of limit. Limit of a constant is a constant. That's the first law. Limit of a constant is a constant. Okay? So let's assume that you have a situation whereby you know this is a constant C. That's a limit of x to x naught of this particular function. Then the answer you get is C. In as much that C is not a function of x. Okay? You can always have this. Limit of a constant and a function. Limit of a constant and a function will give you this, the constant function back. Let's assume that you have something like limit of C of x as x tends to x naught. As x tends to x naught. Then the same thing you obtain is C x naught. Okay? Now imagine, let me give you an example here. Imagine when you say limit x to 5. Limit x to 5 of 7. Your answer is expected to be 7 here. Okay? Since 7 is not a function of x, it does not depend on x. Okay? Limit of, let me give you another example here. You say limit of 5x as x tends to 2. And what do you say? You say 5 times 2, and that's 10. Then the third law of limit is limit of sum is the sum of the limit. Is the sum of the limit. Let's have a certain function, f of x and g of x. You can say limit of x to x naught, f of x, g of x. Okay? Plus g of x. Limit of a sum, you know we have a sum here, okay, is the same thing as the sum of a limit. Limit x to x naught, f of x, plus limit x to x naught, g of x. You can always have an example here. Let's say we have a limit x to 1, 7x squared plus 5x. This is the sum. Okay, we said it is the sum of the limit. Limit x to 1, 7x squared, plus limit x to 1, 5x. And by the time you do this, what do you say? You can always put 1 here. I want to see if I will get the same answer at the right hand side and at the left hand side. Okay? If I put 1 in here, say 7 into 1 squared plus 5 into 1. And you say 7 plus 5. And that's what? 12. So you got 12 here as an answer. L2. Limit of sum is the sum of the limit. Now let's find sum of the limit. Say 7 into 1 all squared plus 5 into 1. You got the same answer, which is 12. So limit of sum is sum of the limit. If you like, you can find the limit while summing it. If you like, you can find the limit of each terms there. That's what I mean by limit of sum is the sum of the limit. Now the fourth law is limit of product is the product of the limit So let's have a certain situation whereby we say limit x to x naught f of x dot g of x. Then we can always say limit x to x naught f of x dot limit x to x naught g of x. So we can always have an example here. Let's say we have a situation whereby we say limit x to 1 over 2 5x squared dot, let's say, dot 3x over x plus 1. 3x over x plus 1. Okay? So we have the product of these two functions. We now said it will be the same thing as separating the functions. Okay, you say limit x to 1 over 2, 5x squared, dot limit x to 1 over 2, 3x over x plus 1. Okay? Then from there, you can always substitute x as 1 over 2 here. Once you see the right hand side and the left hand side will correlate. Okay? We can always say 5 into 1 over 2 all squared dot 3 into 1 over 2 over 1 over 2 plus 1. Okay? From here we say 5. 1 over 2 all squared is 1 over 4 dot 3 over 2 divided by 3 over 2. What do you obtain here? You obtain 1. Okay? And you obtain what? 5 over 4. So our answer for this side is 5 over 4. So let's check around for this side. By the time you put 1 over 2 here, you say 5 into 1 over 2 all squared is equals to dot this. You say 3 into 1 over 2 divided by 1 over 2 plus 1. Okay? So you say 5 over 4 dot 3 over 2 times 2 over 3, or you say divided by 3 over 2. And this will be 1, and you get the same answer as 5 over 4. So the limit of the product is the product of the limit. Okay? The last law of limit is limit of division is the division of the limit. Limit of division is the division of the limit. Okay, so you can always have limit of division is the division of the limit. Okay, so let's assume that we have a limit x to x naught f of x over g of x. Okay, it will be the same thing as limit x to x naught f of x all over limit x to x naught g of x. We can always have an example. Let's assume that you have a situation whereby they say x plus 1 over x squared plus 1 limit x to 3. Okay? So you can always separate it into limit x to 3 x plus 1 over limit x to 3 x squared plus 1. Okay? Then from there you substitute x as 3 here. Say 3 plus 1 over 3 squared plus 1, which gives you 4 over 9 plus 1, 10. 2 here, 2, 2 here, 5. So 2 over 5. Okay, let's say we get the same answer at the right hand side. They say put 3 here, 3 plus 1 over, put 3 here. You get 3 squared plus 1, and that's what? You get 4 here over 10, which is the same thing as what? 2 over 5, same answer. Limit of a constant gives a constant. Limit of the product of a constant and a function gives the same thing. Limit of sum is the sum of limit. Limit of product is the product of the limit. And limit of division is the division of the limit. We'll see the application of limit of functions in the next lectures.